This video is an attachment to the paper entitled Fast Kinodynamic Planning on a Constraint Manifold with Deep Neural Networks. In this work, we consider a problem of planning a feasible dynamic trajectory, taking into account constraints imposed on the joint's velocities, accelerations, and torques, as well as the task constraints, for example, end effector motion restricted to a manifold or collision avoidance. We will present the effectiveness of our approach on two challenging tasks: moving a heavy, vertically oriented object and a high-speed robotic air hockey hitting. The main idea of our approach is to try to find a function which can transform the representation of the problem into a representation of the solution. Particularly, we propose to approximate this function using a neural network and train it using its own experience. Let's see this method in action. Firstly, we focus on kinodynamic planning for moving a heavy object, maintaining its orientation. Our proposed solution is the only one which smoothly moves the gray block from one pedestal to another without collisions. State-of-the-art approaches, even if they manage to reach the goal, they fail to satisfy the task constraints, and their motion is very jerky. This is also visible in the statistical evaluation, as our approach not only has the highest success ratio, but also plans more than 250 times faster than the state-of-the-art planners. Secondly, we test planners in the task of robotic air hockey hitting. The task is to hit the puck as fast as possible towards the goal, while maintaining the mullet on the surface of the table. SST, CBRRT, and MPC-MPNet are unable to satisfy the constraints imposed on the end velocity. Therefore, they cannot score the goal. In turn, trajectory optimization methods manage to score in most of the cases, but still cannot achieve the accuracy and speed of the proposed approach. Our approach achieves 100% score ratio and the smallest planning time. It hits the puck with the highest velocity and keeps the mullet close to the table surface. Our approach can be safely transferred to plan on a real robot without retraining. The quality of plans is similar to the one obtained in simulation. However, due to the higher tracking errors, the scoring ratio is about 80%. Next, we'll show some trick shots. Our planner, thanks to its deterministic planning time and the ability to satisfy boundary conditions, is able to replan the motion on the fly. In this scenario, where robot is moving to score the goal, the puck position changes rapidly. Despite this, robot is able to score thanks to the rapid replanning. In the second scenario, firstly fainting motions are planned and performed, and then suddenly planner replans the motion and robot hits the puck towards the goal. In the first scenario, robot makes some preparatory movements and hits the moving puck. The proposed solution allows to compute a feasible solution to kinodynamic motion planning problem within a single inference of the neural network, plan motions that satisfy various constraints including joint's velocity, torque, and effector position, orientation, and collision avoidance, rapidly replan the actual trajectory and smoothly change to the new one, learn how to plan in simulation and safely apply it on the real robot without additional training, outperform existing constrained kinodynamic motion planning solutions, even the ones that use machine learning.